for mechanical system, and we discussed about the concept of analogous systems. And now in today's class, I shall extend the topic, that is a design or mathematical modeling of mechanical system. And especially I'd like to discuss on a few aspects of modeling that we should remember, because as we all know that in practicality we very seldom find systems which can be accurately represented or properly represented via a linear time invariant model, because in most of the systems are either time varying or non-linear in nature. So in today's class, we shall take a such an example where there is a nonlinearity, and we will discuss in general that how to tackle the nonlinearity and how we can approximate this nonlinear model and represent the system by a linearized model. So in this regard, the example that I've taken is a liquid level system. So to be very precise, it's basically a liquid surge tank. Now, what is the basic principle of a surge tank? The surge tanks are normally uh, tanks with sufficient capacity so that any disturbance that is occurring due to a sudden increase in demand or a fall in supply can be taken care of merely by the volume of liquid that is stored inside the tank. So this is the basic principle of a surge tank. So there is a surge tank. That means if you remember, suppose you want to supply a particular flow rate of water to a varied customers, okay, like municipal water supply. The problem is that if you want to supply that flow rate to a varied customer, where the customer demand will vary, okay, at different times of the day it will vary. So then the problem that will happen that due to change in their demand, okay, there will be disturbances as load disturbances on your supply, and there will be a fall or rise in the flow rate, because instantaneously you cannot take care of the disturbances. To take care of such surge in demand, because if the demand is suddenly appearing and a large amount of demand is suddenly appearing, then we call it surge demand. So that will make a huge fluctuation, a considerable fluctuation in the flow rate. But we want to maintain a steady flow rate. So just to take care of such situations, what is done? The liquid is first stored in a tank. That is called a surge tank, and the supply is delivered from the surge tank. I think you have all seen overhead tanks that are placed in your locality where it is getting supply either from deep boring or from other municipal supplies, and their storage tank will supply the water to your home, because just because of its large capacity, it is basically an integrating type system. That is, any disturbance, be it surge disturbance or a sudden change in the load conditions or the water demand, by its mere capacity, it will take care of that and will make sure that the flow rate can be maintained at a steady level. So for that, one second. So for that, we shall discuss that how we can model such a surge tank. It's a very preliminary and very basic model. As you can see, there is suppose a valve over here which you can operate to maintain the outlet flow rate at any given rate. So suppose the inlet flow rate is Fi and the outlet flow rate is F, that is going through this valve. This can be controlled. You can maintain the flow rate as per your wish. And the volume of liquid within this tank is say V with a height say capital H, Capitalized doesn't seem good, so let's write small h, and the cross-sectional area of the tank is A. Okay? So this is a situation that we have. Now, our objective is to find out a mathematical model for this search tank. To obtain the mathematical model, that is basically what is the system? The system is a liquid in the tank where there is an inlet flow rate of Fi and outlet flow rate of F. The outlet flow rate you can control by a valve. So let us see how we can obtain a model. Now there are two approaches of obtaining the model because there will be basically a material balance that you have to achieve. Now this material balance can be achieved in two approaches. One approach is integral method, another approach is instantaneous method. I'm just giving you these ideas because it's very elementary things and this is the way we normally model any physical system. So let us first consider what is an integral method. So in integral method, the rule that you should follow is that the for the material balance, the first thing is that consider a finite time interval delta t and perform material balance over the time interval. Now, how this material balance equations can be written? For that, you can write mass of water in the tank at T plus delta T minus mass of water in the tank at time T will be equal to mass of water entering the tank entering the tank, and that means the mass of water that is entering the tank between T and T plus delta T, right? I should write between minus mass of water leaving the tank between T and T plus delta T. right? So with this, what we can write, say we have a volumetric flow rate. Fi is a volumetric flow rate at inlet. F is a volumetric flow rate at outlet. Okay, say V is the volume of liquid in the tank, and say rho is the liquid density. Then we can write from the natural balance the water mass of water in the tank at T plus delta T, that is V rho at T plus delta T, minus mass of water in the tank at T minus V rho at T, that is equal to mass of water entering the tank between T and T plus delta T, integration T to T plus delta T Fi into rho mass dt minus mass of water leaving the tank between T and T plus delta T, integration T plus delta T F rho dt. Now if you assume that, or this can be represented as, let's just write down this thing, Fi minus F rho dt, right? Now you can use the mean value theorem of integral calculus. So that will give you that this integral T to T plus delta T Fi minus F rho of dt can be represented as this Fi minus F rho calculated at some value T alpha delta T into delta T, where this alpha, that means you're approximating this entire range of Fi minus F between T and T plus delta T by a straight line of slope calculated at T plus alpha delta T, right? And multiplying with that the time period delta T, right? So using this mean value theorem formulation, what you can write from the left hand side and right hand side, you can write V rho at T plus delta T minus V rho at T is equal to Fi minus F rho calculated as T plus alpha, sorry, alpha delta T into delta T. So divide by this delta T, so we'll get V rho at T plus delta T, V rho at T divided by delta T, right? Now, if we apply over here the mean value theorem of differential calculus. So this will give you d dt of 0, right? And on this side you get this fi minus fi rho minus f rho, right? Why? Because we are taking a limit delta t tends to 0 over here. So we can write this expression. This is the final expression for the dynamic equation. Or if you consider this rho to be constant, then you can write rho dv dt is equal to fi minus f rho, or dv dt is equal to fi minus f. So that means if there is a change in fi, or if the volume of the in the volume of the water in the tank will change, obviously it's very common idea, and how it will change will be determined by this first order differential equation. Similarly, you can write down for height. If you want to measure the height, then this v can be written as h, a being the cross section area, so you can write a dh dt is equal to fi minus f. Again, if you want to measure or if you want to estimate how the height will change, so that will be the expression for height. Now, the same equation, in fact, this is an integral method because it's based on the accumulation of mass over a finite time period delta t, and as this delta t tends to 0, we get this form of equation. Now, there's another approach which is much easier, that is called an instantaneous balance. Instantaneous balance method. Now, this is much more straightforward, and the statement of this instantaneous balance method is that it is based on instantaneous value, that is at any instant of time. So you can write down that rate of change of mass of water in tank is equal to mass flow rate of water into the tank minus mass flow rate of water out of the tank. Now here what you are interested in, instantaneous values of mass flow rate. So what you can write directly from this equation, so you can write that rate of change of mass in water, that is d dt of 0 is equal to mass flow rate of water, that is fi into rho minus f rho. So directly in a single statement, you can arrive at this instantaneous balance method. So obviously you will ask, then if it is so very easy, then why you are wasting our time or concentrating on this integral method? Now, this instantaneous method is only true where you can assume the system to be lumped, or it is a point phenomena, or there is no distribution of mass, or there's no distribution of density, anything like that. Then only you can consider the entire mass to be a unified one, and you can apply this rule. But if there is a mixing available, there's a blending process, then it may happen that at different inlet conditions, there are multiple inlets, and different inlets have different flow rates, and the mixing is not uniform throughout the tank. Suppose in a blending process, then you cannot instantaneously write this instantaneous balance equation. So then you have to resort to this sort of equation where you have to consider the total amount of mass at t plus delta t to find out what amount of mass I've gained from time t to t plus delta t, and that should be equal to the amount of mass entering in the tank through various inputs minus the mass of water leaving the tank through various outlets, right? So in that method, in that scenario, this integral method will be much more suited. So that's why it's very important that you understand both this integral method and the instantaneous method. Obviously, given a very idealized element with no distribution and everything is like lumped parameter or uniform distribution, you can go for instantaneous balance. But the integral method is much more practical, and it can be much more suited for variety of physical conditions or actual practical scenarios. Right. Now, as you can see, the equations that we arrived at seems very straightforward, and it seems okay, fine. We have assumed, we have obtained the mathematical model, and we can proceed with that. Now there is a thing or two that we should point out here. First of all, the outlet flow rate involves a flow through valve. Now we know each and every valve has its own characteristics, and this flow through valve is expressed as F is equal to CV Fx root over CV. Now what are these things? F is the volumetric flow rate. I'll write down. Then this CV is the valve coefficient. Then Fx is the flow characteristics. I'll come to it later. This flow characteristics. Again, this PV or delta PV is the pressure drop across the valve.
Incoming voice call from +917602.
Hello. Yes. Yes. So I'm in a class right now. So please call me. Okay, come up to 1 p.m. 1:30. Okay. So it's a pressure drop across the valve. Then SG is basically the specific gravity of the liquid. The liquid. So this is basically how a flow through a particular valve can be characterized. Now, just to mention, it's not very important. The flow characteristics, it normally varies between 0 to 1. It can have few different value between 0 to 1 as a function of x, and they're basically two or three different functions. That is, if it's a linear valve, then we have fx equal to x. Now, if it's a equal percentage valve, if it's an equal percentage valve, then we have fx is equal to alpha to the power x minus 1, where alpha may be 50. This is not part of our syllabus, but just to mention, because I'll be discussing something more trivial, and there can be a quick opening valve for that fx will be put over x. So this is basically x, where x is nothing but your valve opening. These are a very important thing. X is equal to fraction of the valve opening. Right? So these are the different kind of valves that you can think of. So in a nutshell, what you can say that any flow through valve can equivalently be represented as F root H, where beta is the flow rate constant and root H being the pressure head across the two terminals of the valve. Right? So if I consider this sort of a representation, then let us see how the equation looks like with this assumption. We have already defined that dv dt is equal to fi minus f. So at steady state, now how do we define steady state? For a liquid flow system like in a such valve, at steady state, dv dt should be equal to 0. There should not be any change in the volume. And when it will be achieved? Only when Fi is equal to F. So inlet flow rate is equal to exactly equal to outlet flow rate. And under such circumstances, you will have equilibrium where the height of the liquid or the volume of the liquid in the tank will be constant. So, or you can write that under this considered condition, it will be say beta root H. So this will be the condition under which you have a equilibrium that is reached. Now, let us say a different scenario that what happens if there is certain changes in the inlet flow rate. Now, actually, what happens? Suppose we have achieved a steady state. Say we have achieved a steady state where we have H is equal to 1 with Fi being equal to 1. Now, let us see if inlet flow rate undergoes a step change. Step change. That is, Fi undergoes a step change. That is, Fi, which was initially 1, has now moved on to 2. So, what will be the new steady state valve position? Height, sorry. So, under this condition, you can say steady state height, and we also assume beta to be equal to 1. Say. So, what will be the new steady state height? H S will be equal to 4, right? Now, let us consider another scenario where Fi changes from Fi equal to 1 to Fi equal to 3. Then under such circumstances, what will be the steady state height? Hs, it will be 9, right? Now, these two scenarios will have some distinctive feature. What is that? See, if you consider the first step in case 1, what is the gain of the system? Defined as change in output by change in input. So, in the first case, what was the change in output? That is delta Hs by delta Fis. So, there was change in output 1 to 4. So, 3 by 1 equal to 3. In the second case, your gain was 9 minus 1 by 3 minus 1, 4. See, although it looks like the system is in as unique system, but gain is varying. For a step change in Fi of amplitude 1, the gain was 3, whereas for a step change in input or inlet flow rate of amplitude 2, the gain has become 4. So this phenomena is mainly due to this nonlinear behavior or the valve characteristics. That is, the flow rate is not directly proportional to the valve, rather, it's a nonlinear function, not valve proportional to the pressure head, but it's a nonlinear function of the pressure head across the valve. So therefore, you cannot employ directly a simple ordinary differential equation with constant coefficient to represent such a system, because for different input conditions the gain will be different and it will arrive at different models. So this is typically the feature of a nonlinear system. Okay, because if you look at the equation here, the actual equation is a nonlinear one because of this root h. So now the next question comes in: how do you analyze such systems? You cannot represent such nonlinear systems using a simple ordinary differential equation. So what we have to do, we have to consider a linearized version of this nonlinear equation. Like, linearization of such nonlinear models. Now, so we have seen that the material balance or the energy balance describe the behavior of a process, and if or very often such models are nonlinear in nature. But most of the control strategies that we will be discussing and those who are available in literature, either design or analysis technique, are mainly based on linear systems theory, because it is much easy to apprehend, much easy to utilize, or much easy to use as compared to the nonlinear methods. So therefore, it is important that to start with, we should linearize this model, and so that we can have a option to apply this comparatively convenient tools which are present for linear systems. Okay, so this linearization method that you shall consider is based on Taylor series expansion. Now let us see what does it mean. So in Dealing with, we shall consider different scenarios. Number one scenario, there is only one state variable. That means a single variable equation in the form dx dt is equal to fx, which is a nonlinear equation, obviously. Okay. Now, the very concept of this linearization is based on the fact that if you have nonlinear behavior, like say this one, why I'm calling this a nonlinear behavior? Because if you draw the tangents at different points, there are different tangents. As a result, the nature of the response for a given input at this individual points will be completely different. It's a nonlinear function, right? So what you can do, obviously I should mention here, say this is the input, this is the output. So what we can do, we can consider a operating point. What is called an operating point? Say over here. So if we consider a very narrow region around this operating point, say this region, within this region, see, we can approximate this blue curve by this straight line segment, right? So this is called piecewise linearization about an operating point. Now, what is the basic concept? Basic concept is that if you consider this neighborhood that I marked in red to be narrow enough or small enough so that for any perturbation within this neighborhood will cause the system behavior to behave, a system to behave in a linear fashion. See, it is behaving or it can be approximated by this straight line segment. So any change within this range can be approximated by this linear or this straight line. So if you consider this operating point, which is again a steady state operating point, and if you identify this steady state operating point, then the process will be linearized in this small neighborhood around this steady state nominal operating point by a gradient, that is the slope of the straight line, which is indicated by this small segment of straight line. So we can consider the system to behave in that linear fashion only within this operating region. And we can consider this particular model valid in the defined neighborhood about that particular operating point. In a similar fashion, you can assume another operating point, say over here, and define another neighborhood like this, where it can be approximated by this straight line segment. So around this operating point, you get another mathematical model. So it will be different. The whole line of slope change हो जाएगा. But this model will be a linear model around this steady state operating point, which is called also a nominal operating point. So that is the basic theme, that you assume a operating point and take a neighborhood around that operating point. The neighborhood should not be small enough so that it doesn't give you much freedom, or it should not be large enough so that the system linearity will be lost. So you have to adequately choose a neighborhood such that within this neighborhood system behaves in a linear fashion. So if we assume that, and this fx now can be approximated as f of x's, that is fx evaluated at that operating point, plus into, it is into it, and so on, and higher order terms. This is basically the Taylor series expansion about the operating point. Since each and every derivative, first order partial derivative or second order partial derivatives, are calculated about the operating point or the steady state operating point around which we are trying to linearize. Now, by neglecting this second or higher order terms, this can be approximated as f of x's del x minus x's. Right? Now, what is fx? Fx is basically dx dt. So you can write dx dt is approximately equal to del fx del x at x equal to xs. What about fxs? Because since fx at x equal to xx is equal to 0, because at steady state operating point your dx dt लिखेगी. Understood? That means this fx will be 0. So this can be approximated like this, multiplied by x minus x's. Right? So solve later. So if I write down fresh, so you can write dx dt is equal to del fx del t, sorry, del x at x equal to xs multiplied by x minus xs. Now, since xs is a constant, we can write d dt of x minus xs, because right, since xs is constant, so this can be equivalently represented as dx dash t, not x dash t, you should not write this, the confusion বেড়ে যাবে, dt is equal to some constant x dash. Now what is this x dash? X dash is equal to x minus xs. So this is deviation variable. Deviation variable means, say x, xs is a constant value, which is nominal value of x, and xt is the instantaneous value of x. So the deviation variable will give you an idea about how much the x has deviated from its nominal value at the current instant of time, right? And this gain a can be calculated as del f del x at xs, right? So this is how we can obtain a linearized model of a nonlinear equation. And this is the linearized model in terms of the deviation variable. I'll give you an example. Let me finish all these things. Now, what happens if your system has one state variable and one input, one state variable, sorry, and one input. That is, your dx/dt is a function of x and u. Then, following the same method, the Taylor series expansion can be written as f of xu is equal to f of xs us, where this is the nominal value, nominal steady state value, xu del x calculated at xs us xs plus del u calculated at xs us u minus us plus all the higher order terms. Now, if we eliminate the higher order terms and following the same principle, we can write in terms of deviation variable dx dash dt is equal to ax dash plus du dash, where x dash t is equal to xt minus xs, u dash t is equal to ut minus us, a is equal to del f del x, and right. This will be much clearer once I give you an example. And what about the output finally? For output variable, what you can write? Say yt given as g of xt ut, some function. Now the Taylor series expansion of this yt and neglecting the higher order terms, you can write is approximately equal to g of xs us plus del g del x xs us x minus xs plus us, neglecting the higher order terms, or simply you can write should be y, should be y, should be only y dash is equal to cx dash minus du dash, where y dash is equal to, just to make sure it's a time varying function yt minus ys, and x dash is equal to x minus us minus us, and c is equal to, and d is equal to, right? This is a very simple thing. Now with this in mind, let us try and linearize the dynamic equation that we derived for our surge tank, liquid surge tank. Obtained as a dh dt is equal to fi minus c root over h. So only nonlinear term is in root over h. So what I have to have? So linearize root over h. So root over h can be approximated as the nominal operating point plus del of root over h calculated at h minus hs. So that is root over hs plus 1 by 2 root over hs, h minus hs. So with this, the linearized model becomes a dh dt is equal to fi minus asserting beta na, beta root h, that is fi minus beta root over hs plus 1 by h minus hs. So after suitable manipulation, you can write down finally it's a differential equation on h. So I should identify the linear part of h, that is first the constant part fi minus beta root h's into h minus beta root h's by 2. So basically it's a function of h, fi, and some constant is. So this is the final linearized model. Why it is linearized? See, there is no root over h term present. Root over h's is a constant. Okay. So what you can write further, if you want to find out the deviation variable model, what you can write that at steady state, okay, if you write down at a steady state or in terms of deviation variable, in terms of deviation variable, then we written as h can be represented as h minus hs. So a dh dash dt is equal to fi dash minus c by, sorry, not c, 2 root h's h dash. Now, how am I arriving that? Arriving at this equation? Let me show you. So, I'm just writing this. Actually, লিখো তোমরা প্রপার রিলেট করতে পারো। এবার এই ইকুয়েশনটা কি করে আসছে সেটা দেখি। How do I arrive at this deviation variable model? To arrive at the deviation variable model, you have to first obtain at h equal to hs. What you can write? A dhs dt is equal to FIS, that means the steady state, nominal steady state, minus C, not C, root H's, root H's. Just I'm writing this over here. Beta by 2 root H's, 2 root H's into H's, or beta root H's by 2. And steady state. There is a steady state. Now dynamic model, what do you have a dynamic model? The dynamic model that we have is A dh dt is equal to Fi minus B 2 root H's by H minus B root H's by 2. Say this is equation number 2 and this is equation number 1. So by 2 minus 1, what you will get? A d of H minus H's t is equal to Fi minus Fis. এবার দেখো these are constant, এটা এটা cancel out হয়ে যাবে. So one thing will be left will be minus beta by 2 root h's h minus h's. 2 থেকে 1 বিয়োগ করছি. So that can be equivalent to written as Fi dash so this is the final deviation variable model of the system. It's a linearized model of the system. Nominal steady state operating point Hs Fis. Yes. So this is how we can arrive at a linearized model given a nonlinear characteristics. দেখো আমরা লিকুইড সাস ট্যাঙ্কের প্রবলেম শুরু করেছিলাম which at first go seemed a very basic thing, কিছুই ছিল না. Then we found out the integral by integral method or instantaneous method the dynamic equation is A dSdt is equal to Fi minus F. Same thing এবারে simplify করে লিখতে পারো since rho is constant, so dv dt is equal to Fi minus F. So same dynamic equation. So although it looked like a very simple dynamic equation, but at its core, we found out that due to the valve, involvement of a valve, which normally gives us a nonlinear relationship about the flow rate to the valve, so we obtained a nonlinear equation. So we have to linearize this equation. To linearize the equation, we followed a Taylor series expansion method, and by this Taylor series expansion method, we finally arrive at the linearized model of the plant. Around whenever we are talking about the linearized plant model, we should always specify the steady state operating point. Nominal or steady state operating point. If you do not specify this, you are not correct. Because see, whenever you change this value of Fs or Hs, Fis or Hs, this coefficients will change. This coefficient will change. If you change the value of Fi, the coefficient will change and the model will be completely different. Right? Beta by 2 root Hs coefficient is changeable. So keep this in mind. So whenever you're defining a linearizing a model, it should be around the operating point. Okay. Now with this in the back of our mind, we should, and this is a very representative diagram for this system. See, here Q bar, H bar, and Q bar, they represent the nominal steady state values, and small qi, h, and q0, they represent the deviation. Qi represents the deviation in inlet flow rate. Corresponding deviation in the height of the liquid tank is represented by small h, and consequently the outlet flow rate will deviate from a steady state value q bar by an amount q0. Now our objective will be to find out a relation between this qi, q0, and h, and that will be the dynamic model for this system. Now, how do you obtain that? See, now before we start discussing about this, we should make one thing in clear, that in analyzing a system that involves fluid flow, so first we have to divide the flow regime. We know there are basically two types of flow regime: there's laminar flow and turbulent flow, and this is determined by the Reynolds number, or the magnitude of the Reynolds number, right? So, in case of a laminar flow, the fluid flow normally occurs in streamlines, and it doesn't normally show any turbulence. So, the systems which involve this laminar flow can be represented by linear differential equation. So, for laminar flow, we can have linear differential equation. For laminar flow, I'm not talking about bulk, the flow. But the industrial processes, they very often involve flow of liquid through different connecting pipes and tanks, and in most of the cases, this flow is turbulent and not laminar. Therefore, such systems involving turbulent flow, they need to be represented using nonlinear differential equations, unlike the laminar flow. Now, just recapitulating the concept of linearization, if the region of operation is limited, or if you can ensure that your region of operation is limited, that is, there would not be much deviation about the steady state operating point, then such nonlinear differential equations can be linearized around that operating point, and we can use that linear model as if we are modeling for a laminar flow, provided that simplifying assumptions are valid. Right, so we'll see how we can obtain a mathematical model for a fluid system that we have assumed here, that is discussed here. So for this liquid flow system, Q bar, as I mentioned, is the steady state flow rate before any change has occurred. Qi is a small deviation in the inlet flow rate from the steady state flow rate. And corresponding to that, Q0 will be the small deviation of outlet flow rate from its steady state value, Q bar, where H bar was the steady state head before any change has occurred, because at steady state, inlet flow rate was Q bar, our capital Q bar, outlet flow rate was capital Q bar, so height was constant at H bar. Now there's a change in inlet flow rate by amount small qi. So that will cause a change in the height by small h about h bar, capital H bar, and that will cause a change in the outlet flow rate by an amount q0. So we have to model this entire operation, okay, and see how it can be modeled. So to model this, what you can do, let me copy this, right? Now, as I have stated previously, that the system will be considered linear, that is, the flow is laminar, or if it is turbulent, we'll linearize the equation by keeping in mind that the variations in qi, h, or q0 get very small. Okay, so in either case, be it a linearized one or be it a completely linear system by itself, we'll try to obtain a differential equation for that. Now, how it can be obtained? Since the inflow rate minus the outflow rate during any small interval dt will be equal to the additional amount of stored water in the tank. So you can write C, that is capacitance of the tank, into dH will be equal to Qi minus Q0. There is a net amount of fluid accumulated per unit time into dt. দেখো লিখতে পারি infinitesimal small time delta t. Now, if you remember what is the capacitance, how it is defined, change in liquid stored in volume meter cube divided by change in head in meter, right? Now, from the definition of resistance, how is resistance defined? Change in level difference divided by change in flow rate, that is meter meter cube per second. Now, what does resistance means? That is, it is the change in level difference that is necessary to cause a unit change in flow rate. Similarly, for capacitance of a tank, it is defined as change in quantity of stored liquid necessary to cause a unit change in the head of the liquid. Right? So, based on the definition of resistance, where you can write Q0 is equal to, there is an incremental increase in the outlet flow rate will be equal to H by R. So if we put it over here and take it like this, so C dH dt is equal to Q0 minus H by R multiplied by R. So RC dH dt plus H is equal to RQI. So this is the dynamic model of the system. I've considered all this to be linearized or linear. So if you take the Laplace transform, then you can find out that the transfer function of the system, that is Hs by QS or QIS, that is inlet flow rate, QIS, will be R by RCS plus 1. And let me write on the next page. How does the height of liquid in the tank vary with respect to change in the inlet flow rate given by R by RCS plus 1? Again, Q0S from this definition is equal to HS by RS, HS by R. So that implies the change in outlet flow rate due to change in inlet flow rate will be defined by the transfer function RCS by 1, which, if you remember, is typically right a RC circuit. So where RC is the time constant of the system, and it will show or it will depict how much time it will take for the outlet flow rate to reach the steady state. Suppose the inlet flow rate was here and it took a change up to here. So corresponding outlet flow rate was initially here and it will reach a value obviously over here, and it takes a change over time like this. Q0T, and the red one is QIT. And this is defined by this sort of a time response. Right? Now, since we have now designed for a unit surge tank, let us see a scenario where there is a liquid system involving interaction. There is two surge tanks are in cascade and they interact with each other. And we know the first for the first surge tank, the transfer function will be G1S 1 by R1 C1S plus 1. And for the second tank, plus 1. Now, what will be the overall transfer function? The overall transfer function GS obviously will not be equal to, if we remember, we have done this already for two RC circuits in cascade, right? And we'll do it over here again. How? For that, we show this. For that, we need to write down the different equations. See, first of all, for this tank 1, we can write Q1 is equal to H1 minus H2 by R1. This is Q1. Because following a change Q in the inlet flow rate, height has increased by an amount H1, and that has caused a flow rate Q1, which has caused a height increase in tank 2 by H2, and the dynamics C1 dH1 dt will be equal to net flow rate Q minus Q1. This is for tank 1. For tank 2, we can write Q2, considering it to be linear one, is equal to H2 by R2, and C2 dH2 dt. How much will be there? Inlet flow is Q1, outlet is Q2, Q1 minus Q2. So these are the two very fundamental differential equations. Now, if I try to find out the transfer function, that is Q2s by QS, you'll found out this to be as you have done previously by solving these two equations or taking Laplace transform. Now let us see how we can achieve that. So I'll leave this part, analytical part for you. Now I'll try to arrive at this transfer function by some other approach. Okay, a new approach. Let's see how. Now, what are the equations that I've already written? That H1 minus H2 by R1 is equal to Q1. So taking Laplace transform, H1s minus H2s into 1 by R1 is equal to Q1s. So if I represent this in terms of a block diagram, what I can write? I'm omitting the H1 now. If this is H2 multiplied by 1 by R1. Okay, let me use the block diagram that I already obtained here. Um, I have a note ready, so I'll just share from there. Okay, so this, see, H1 minus H2 into 1 by R1 equal to Q1. Then the second expression Q2 is equal to 1 by R2 H2, right? So Q2 equal to 1 by R2 H2. Next, Q minus Q1 equal to 1 by C1s H1, because see, I have, let me write down this, C1 dH1 dt is equal to Q minus Q1, that is C1 S H1 S is equal to Qs minus Q1s. So if you have Qs minus Q1s, Qs minus Q1s divided by C1s or multiplied by 1 by C1s, you'll get H1s. So Qs minus Q1s into 1 by Cs is H1s. Similarly, from this Q1s minus Q2s into 1 by C2s is equal to H2. Q1 minus Q2 by 1 by C2s is equal to H2. So these are the four equations which is represented in the form of their individual block diagrams. Right? Now if I want to collaborate all of them together, see, I'm just keeping it over here. Now I'm trying to collaborate all these blocks together. Now how I'm doing that? See, QS is my input. So I put QS over here. And I know if I can subtract Q1s from that and multiply by 1 by C1s, I'll get H1s. Now, from H1s, if I subtract H2 and multiply by 1 by R1, I'll get Q1s. Coming to this, if we have Q1s and subtract Q2s and multiply by 1 by C2, I'll get H2s. Agreed? And finally, if I have H2s, multiply by 1 by R2, I'll get the output Q2s. দেখো বুঝতে পারলে ব্লক ডায়াগ্রামটা? ঠিক আছে? এই প্রত্যেকটা ক্লাসটা দেখো লাল দিয়ে প্রথমটা করেছি এটাকে, সেটা হচ্ছে দিস পার্ট। সরি, এই পার্টটা হচ্ছে এইটা। নেক্সট এই পার্টটা করেছি, এখানে উচিত না, এটা নিয়ে করেছি। নেক্সট এই পার্টটা এখানে Q1 পেয়ে গেছিলাম, সেটা Q1 মাইনাস Q2 H2 and finally এই পার্টটা H2 Q2. So this is the block diagram representation of this system. খেয়াল করো, there are multiple feedbacks. One loop is over here. এখানে একটা ফিডব্যাক আছে, এখানে একটা ফিডব্যাক আছে, তো দুটো two feedback systems are in cascade. What is the transfer function of this? If we neglect this, so this feedback system transfer function will be 1 by R1 C1s or I can simply draw this. এর একটা ফিডব্যাক আছে এটা, আর সেকেন্ড ফিডব্যাকটা আছে কিরকম, এর সাথে ক্যাসকেডই আছে বেসিক্যালি। দেখে তোমার কাছে খুব সিম্পল হয়ে গেল না, এইটুকু হলে তো জাস্ট মাল্টিপ্লাই হয়ে যেত, কারণ দিস ট্রান্সফার ফাংশন ইজ 1 by R1 C1s plus 1 আর দিস ইজ 1 by এটা প্লাস 1 করে দেখো আবার R2 C2s plus 1. But the problem is due to the presence of this, দেখো এটাই হচ্ছে যেটা যেটা দুটো লুপকে মাঝখান থেকে জুড়ে দিচ্ছে। এই পাঁচটা, so this is the interacting part via the feedback H2. So that is why we're actually seeing that the transfer function will not be R1 C1s into R2 C2s, but R2 C1 will be there as a part of interconnection. বোঝা গেল তাহলে? এবার জাস্ট আমি দেখিয়ে দিচ্ছি, পরের দিন ডিটেলসে আলোচনা করবো ওটা, পিডিএফ থেকে দেখিয়ে দিচ্ছি, দ্যাট ইজ হাউ টু রিডিউস দ্য ব্লক ডায়াগ্রাম। এটা হচ্ছে অরিজিনাল ব্লক ডায়াগ্রাম that we have. Now this can be re-altered in this fashion. তাহলে কি হচ্ছে দেখো, এইটা একটা ইন্ডিভিজুয়াল লুপ তুমি পেয়ে যাচ্ছ, এটা লুপ, আর এইটা একটা লুপ, ঠিক আছে। আর এই যে বাইরেরটা সেটা কিন্তু দুটো লুপের বাইরে দিয়ে আছে, ঠিক আছে। তার জন্য কি হচ্ছে, খেয়াল করো, এই লুপটার জন্য এই ট্রান্সফরমেশনটা পাচ্ছি, এই লুপটার জন্য যেটা বলছিলাম এই ট্রান্সফরমেশনটা পাচ্ছি, বাইরে দিয়ে আরেকটা ফিডব্যাক আছে, দেখো এখান থেকে গিয়ে এখানে সেই ফিডব্যাকটা এখানে। So since they are in cascade, এর ট্রান্সফরমেশনটা কি হবে, ইনটু, তাই তো। এবার এর সাথে ফিডব্যাক পার্টে কি আছে, R2C1S। সো এটা আমাদের ক্লোজ করবে, গেট ট্রান্সফরমেশন লাইক দিস। এবার এই জিনিসটা তো খুব বলে দিলাম যেভাবে ইট ক্যান বি রিডিউসড, তাহলে দেখে হয়তো মনে হতে পারে ইটস নট দ্যাট easy to apprehend, but in the next class we shall discuss about this block diagram reduction technique in detail. Okay, and we'll try to solve a few such complicated problems where we have to deduce the block diagram to finally obtain a transfer function between input and output in a simple fashion. So this is your closed loop transfer function, right? ঠিক আছে, আজকে তাহলে এইটুকুই থাক। বলো, কার কোনো প্রশ্ন আছে, এনি ডাউট? Okay. So I'll stop here today, and in the next class we shall discuss only about the block diagram algebra, and then we shall proceed with the time response analysis and all.